Hello everyone, class 12th, and the topic is Balz-Schiemann reaction for fluorobenzene. Yes, fluorobenzenes can be generated from Balz-Schiemann reaction, another name reaction, very important. Let's write what that reaction is. Firstly, we need aniline. We are going to react it with sodium nitrite and HCl, hydrochloric acid. Temperature must be 0 to 5 degrees Celsius. In this condition, it will give you benzene diazonium chloride. Benzene diazonium chloride. The compound is highly unstable. You can check, nitrogen is carrying a positive charge, 3-4 bonds are over there. That's why the compound is highly unstable. So to keep it, we need a low temperature. Otherwise, if I will increase the temperature, its bond will break. Obviously, bond will break from here, nitrogen gas will release out, and this compound will decompose. That's why to maintain it, we require a very low temperature, 0 to 5 degrees Celsius. Now, that molecule is going to react with fluoroboric acid, HBF4, and will turn itself to this molecule. In fluoroboric acid, H positive, BF4 negative is there. So this negative particle, this nucleophile is going to substitute this nucleophile and will turn itself to this one. We call it benzene diazonium tetrafluoroborate. Benzene diazonium tetrafluoroborate. This is benzene, this is diazonium part. This is tetra. Tetra means 4, fluorines are there, and borate is for boron. This one. Now, final step, the compound is completely unstable. On heating little bit, you will heat, you will get fluorobenzene as a final product, and the side products will generate out nitrogen gas, N2, and BF3. Here I am writing BF3. These are the side products. Out of BF4, 4 fluorine, 1 fluorine will join on benzene ring, and BF3 will release out as a stable product. Nitrogen gas will release out, and finally we will get fluorobenzene. So this is whole reaction we have, which we call Balz-Schiemann reaction for fluorobenzene. Check it. First step, second step, and third step. 3-step reaction it is. Generation of benzene diazonium chloride from aniline, then generation of benzene benzene diazonium tetrafluoroborate, and finally heating it to create fluorobenzene, nitrogen gas, and BF3. Now let's check its mechanism. The very first step, generation of step by step I will talk about. Like aniline was there, NH2, we reacted it with NaNO2 in the presence of HCl, which create this one, benzene diazonium chloride. Its mechanism we will understand first. Let's talk about this mixture. NaNO2 plus HCl. Na is positive particle, NO2 is negative particle, H is positive particle, Cl is negative particle. H will combine with negative, Cl will combine with positive. So side products will be HNO2, nitrous acid, and NaCl. Sorry, I used side product word. It's the main product, nitrous acid and NaCl. Now, nitrous acid, its bonding is like this. This is nitrous acid. Now we know other particles of HCl are also available. HCl. One particle I have used to react with NaNO2 and nitrous acid is generated, but more HCl particles are available. HCl is also acid, nitrous acid is also acid, but out of HCl and nitrous acid, this is strong and this is weak. So strong acid will liberate out H positive easily. Now these H positive will start attacking on lone pair of electron on oxygen. This is H positive, a electrophile, need electron. Oxygen is available there with a lone pair. So it will turn itself to HO, H, and O. This oxygen already carry a lone pair, and this nitrogen is also carrying a lone pair over there. Now, when oxygen will make bond with this hydrogen, it's a dative bond. Means it is using its lone pair to make bond with hydrogen. One electron it will transfer toward H positive. That's why this oxygen will carry a +1 charge. Unstable condition. Now in this unstable condition, it will break bond from nitrogen like this. And it will change itself to, from here bond will break, H2O will generate out, and this nitrogen which is losing its electron, this electron, it is losing, so it will have a vacant orbital there with a +1 charge. Nitrosonium ion. This is the main intermediate which is generated over there, nitrosonium ion, an electrophile. Now look what will happen after it. Up to here there is no problem. Nitrosonium ion is generated. It's an electrophile which need electron. Who can provide electron to it? Aniline is waiting. In aniline, nitrogen have a lone pair, and this nitrosonium ion need that. This vacant orbital will attack on nitrogen. Now you can check. Dative bond will generate like this. Now after this dative bond, this nitrogen who has attacked on it will become neutral, but this nitrogen will be in the problem because it is giving one electron for the bond formation completely toward this nitrogen, so it will carry a +1 charge. Unstable it is. Now how it can get stability back? By breaking bond from hydrogen. This hydrogen will release out as H+1. H+1 is an electrophile, want electron, it will go for oxygen side, pi electrons are available there, like this. After this, we will get this condition. Now this nitrogen will get lone pair, hydrogen is there, this. In this condition, this oxygen is going to make, check properly, this is the lone pair. If one lone pair it is using with H positive. For stability it will break bond, pi bond, and shift electrons back toward it, due to which this will happen. Pi bonds are shifted toward oxygen because oxygen is more electronegative than nitrogen. So it is getting the pi electron, and this nitrogen will again be in problem. Positive charge, vacant orbital. Now neighbor nitrogen again will help to it. How? By breaking bond from hydrogen and shifting this bond toward nitrogen like this. What will happen now? Between these two nitrogens, lone pair is as it is. Please keep watching these lone pairs. Double bond will generate, and this nitrogen will stabilize, and this hydrogen will eliminate out again as a H positive. The H positive particle again need electrons, will go for oxygen. Again the same process will happen. Two hydrogens will join, and oxygen is going to make coordinate bond with this hydrogen. In this condition again oxygen will become unstable, and finally it will again break bond from nitrogen like this, and again this nitrogen will be in trouble because it is losing electron So again plus 1, and what will release out? H2O, stable product. Now, third time again this nitrogen will help its neighbor. Lone pair, vacant orbital. Through lone pair and vacant orbital, between them a bond will generate. Like this. But itself this nitrogen will be in problem because it is making dative bond. So one electron will be completely toward this nitrogen, due to which this nitrogen will get complete plus 1 charge, and this plus 1 charge is stabilized by Cl negatives which are available in reaction through HCl. That's it. This is the generation of benzene diazonium chloride. Whole process that we have, whole mechanism for the generation of benzene diazonium chloride. Now after this, what happened next? Second step was in Balz-Schiemann reaction, reacted with fluoroboric acid, and we got BF4 negative. So I believe that we don't require so much information for that. It is just a nucleophilic substitution reaction. Cl negative is replaced by another nucleophile, BF4 negative, and HCl will be a side product. This is benzene diazonium tetrafluoroborate. This one. Now just Cl negative is getting replaced by BF4 negative. This is fluoroboric acid, H positive, BF4 negative. It is separated. These are acids. Obviously acid will release out H positive. So H positive and BF4 negative. BF4 negative is replacing Cl negative, and this Cl negative is going to combine with H positive as a HCl. Now the last step of the reaction. This benzene diazonium tetrafluoroborate, we will heat. This positive charge is balanced by BF4 negative. We are heating this molecule. As I already told to you, this molecule, benzene diazonium, it is highly unstable. To keep it with us, we need a lower temperature, 0 to 5 degrees Celsius. But what we are doing, we are heating. Now on heating, obviously, weak bonds means unstable bonds will break out and stable compounds will generate. Okay. How this nitrogen can get stability? It is very clear. If it will break bond from carbon like this, obviously both electrons will go toward nitrogen because nitrogen is more electronegative than carbon. So this bond will break like this. And let's check about BF4 negative. What is BF4 negative? It is in this condition. This one. Around boron, we have 4 fluorines. Out of 4 fluorines, 3 are making normal covalent bond and 4th is making dative bond. Due to that dative bond, it is getting a -1 charge. This boron is getting -1 charge. Now when we will heat it, obviously boron is stable with making 3 covalent bond. The 4th bond is forcefully made by fluorine, which is dative bond. So when you will heat it, this dative bond will break. And when bond will break, both electrons obviously will shift toward fluorine because fluorine is more electronegative than boron. So finally, boron will become free from that dative bond and vacant orbital will generate. A neutral boron will be eliminated out. What about fluorine? Because it got 1 electron, so it will release out at fluorine negative, F negative. So check. From here, nitrogen will break bond from carbon and carbon will get a positive charge. This positively charged carbon will be attacked by this negatively charged fluoride. And what will generate? Fluorobenzene. What about this nitrogen? Nitrogen is gaining 1 electron already. This nitrogen have a lone pair. It will also get an electron. So it will release out as like this in this condition, nitrogen gas. N2. And what about BF4 negative? BF4 negative turned itself to BF3, boron trifluoride. Out of 4 fluorine, one fluorine is joined with benzene ring to create fluorobenzene. This is the whole mechanism we have for Balz-Schiemann reaction. It's a 3-step process. Thank you very much for watching the video.